Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Hello, lesson 13. Hello there. How do 3D printers work? All right, classwork opening exercise. Observe the following right circular cone. The base of the cone lies in plane S, down here, and planes P, Q, and R are all parallel to S. Plane P contains the vertex of the cone. So the very tip of the cone is touching plane P. Okay. So now it says to sketch the cross section P prime of the cone by plane P. Okay, so what they're saying is if you were to take a cross section at this level, what would that look like? Well, what would it look like? If my pen would work, I could show you. It would look like that. It would just be the dot where the vertex just touches plane P. Okay, so that's all that would be, a dot. Then it says, move down to Q. So here they aren't showing the cross-section cutouts, they're just showing the levels of where the planes are. But over here, they darkened what they're cutting out, going with the cone going through that plane. So then it says to sketch the cross-section of Q prime of the cone by plane Q. All right, well, in order for us to do that, you can just draw a circle, but I am going to do it this way, and it would be a circle of roughly that big around, and I'm going to shade that, and I'm going to make it thinner, by the way. So let's go like this. Line colors, black is fine. Fill color, it looks like a really light green, maybe this one. And then let me switch to really thin. So there, that is what the cross section of Q would look like, a circle. Okay, and then if we sketch the cross section of R prime of the cone by plane R, so that's down here, it's another circle, but it's larger. So I'm going to draw another circle. Let's make it thin again. Draw another circle, and it would probably be, oh, I don't know, about that big. And it is purple, so I will shade that with purple. Just so we know which we're cutting out of. Okay, so that doesn't really look right. There, that'll work, I guess. Okay, and so that is the cross section R. Then it says sketch the cross section of S prime. That is the base. Well, the base is obviously a circle as well. So it is larger. So let me do this and let me center it better. So if you had a compass, that'd probably be the best way to do this. I have the tool that I'm allowed to cheat, if you will. And so there's that. And let's make that fill color kind of like the base, which is kind of this peachy color. Isn't that peachy? All right, so let's recap now. So if we're looking down on this and we cut a cross section out at the very top, you're just getting a point. You go down a little further, the circle's getting larger, the cross sections are getting bigger, but they are circles, so long as they are parallel to the base. So those are cross sections of this cone. Okay, page 2, B. What happens to the cross sections as we look at them, starting with P prime and work towards S prime? So if I go back to this page, what happened as we started at P prime, went to Q, then to R, then to S? Well, what do you see happening? All right, well, here's what it is. The intersection of plane P with a cone is a point, and each successive cross section is a disk of greater radius than the previous disk. All right, exercise 1. Sketch 5 evenly spaced horizontal cross sections made with the following figure. Sketch 5 evenly spaced horizontal cross sections made with the following figure. This is an exercise and I will pause the video and you try it. Okay, so right here, as you can see, there is a hyperlink to a website. So I decided to go to that, and it was made with MATLAB, public domain. All right, so it says attribution not legally required. All righty, so I'm going to show it. So here it is. Okay, this is what it looks like if you hollowed it and you could see through it, these rings going all the way around. So maybe if you haven't done this yet, now we're doing horizontal cross sections. Okay, all right, so let's see what goes on there. Okay, so if I were to just cut this out and just do the piece that's touching the floor, if you will, well, what would that look like? It would look like a circle. Let's do it in green since it's a green object on our screen. It would look like a circle, but it wouldn't be solid. Fill color, none. Line color, green. All right, so that's what it would look like, just the little bit that's touching. All right, and if this is solid, actually let's do not solid first. So then if I went up a little bit, and let me make the line thin and let me make it green right from the start. If I made it not solid, so that would be fill color, none. Then I would have a circle that would be larger than the original, but also another one that wouldn't be as large as the original. So if I just went up a little bit and cut this out, it would look like this, sort of. Yeah, that's better. It would look like this. Let's change it to green. No, not fill. Let's not get to the fill color yet. Okay, so it would look like this if it were hollow, like this. You would just have the two walls where they touched the plane that you cut. Agreed? Okay, but let's assume that this is solid. Well, if this is a solid object, then we would fill in between. And I'm not certain. Yes, I can do that. So I'll go like this. No, the bigger one. And I will fill it green, like so. So there it is. That's what it would look like if this were a solid piece. Okay, so what happens if we get up to the center here where it's the largest radius? Well, we would have the same thing. So, okay, so it would look like this. It would be thicker from the outside edge to the inside edge, and it might even be thicker than that. It might even look more like this, but then I'd have to move this down because it's not centered. Something like that maybe. Okay, so that would be like at the center. Now we're moving back up. The thing is going to start getting smaller again. So I'm going to just copy this and put it over here, and then copy this and bring it over here. Try to center it. Okay. Something like that, roughly. So these two would look about the same. That's about right there. And then finally getting to the top, we would end up with a similar looking slice. So slicing it right at the bottom left, working our way up until we got to the maximum diameter, if you would, in the center, and then tapering back down. And then the top plane would just be a circle again, like so. Alrighty, so there are the cross sections of this donut. Okay, page 3 brings us to an example, a little bit more challenging. It says, let us now try drawing cross sections of an everyday object, such as a coffee cup. So here's a coffee cup. Sketch the cross section at each of the indicated heights. So height 1 is the top. So if we're at height 1, we're just on the rim of the cup and that would look like a circle like so. So there's the top of the cup. Now, if I come down further to 2, it should be a little bit larger and probably a little bit thicker. So that would look like so. So this is the solid cup. This would just be the rim. And then number 3 is right here. And notice it is hitting the handle as well and coming right through the handle. So it's being extended out like the handle there. So if you look down on that, it would look like this circle here, maybe a little smaller because the cup is tapering. And then this handle would be jutted out off to the side here. So that would look like this. So here's the handle. And then number 4, you would have something that looked like 2 right here, but then you would have a piece of the handle out here, but nothing in between because we're cutting through air. And that would look like this. So here is the cup, and then over here is the space, and then you're hitting the handle again. Okay. And then finally 5 is the base, which would look like number 1, except it would be solid. And there is the base of the cup. So those are our 5 cross sections of this coffee mug. Okay, page 4 brings us to exercises 2 through 4, but actually just 2 and 3 are on this page. And before I get there, this lesson is called How Do 3D Printers Work? So there's a video here of 3D printer general. It says http computer howstuffworks.com 3D printing.htm. If you type that in and go to this website, there's actually a 13-minute video that's pretty cool, and it's recording a coffee cup being created by a 3D printer. So I would recommend that you watch that to see how a 3D printer works. What it does is it layers horizontal cross sections of an object and piles them on top of each other until it becomes a 3D object. All right, so number 2 is a cone with a radius of 5 centimeters. So a cone. For starters, I need to underline all the information that is important. So we have a cone. Radius 5 centimeters, height 8 centimeters. Is to be printed from a 3D printer. The medium that the printer will use to print, i.e. the ink of the 3D printer, is a type of plastic. So the word medium is what they call the material that they put in the printer. So the medium is a plastic that comes in coils of tubing that has a radius of 1 1/3 centimeters. All right, so that's more information that I need. So I'm going to highlight that. Coil tubing, radius of 1 1/3 centimeters. Okay, so we have 2 different objects. One I underlined in red, one I highlighted in yellow. So the first thing I would like to do, I always like to draw a picture to get an illustration. So I drew a picture of a cone, and here it is. And if I draw a radius from here over, there's my radius. The radius is, and I label my diagram, the radius is 5 centimeters. And the height is 8. So this is the height in the center. That is 8 cm. Okay. All right, so that's the cone. That's what we're going to print. The tubing we're going to use is right here. So if you take coil tubing and straighten it out, that wire looks like a cylinder. And I don't know if you can see that little red line right there, but that's the radius, and R equals 4/3 centimeters. I just wrote above there. So there's all the information, and now we need to put this together. So a cone, so we need to find the volume. So we need the volume of the cylinder and the volume of the cone, and they need to be equal. That tells us how much of the cylinder will make this cone. So the volume of a cone equals 1/3 base area times height. The volume of a cone equals 1/3 The base is a circle. That's the base area, capital B. That will be pi r squared, and then times the height. So you see how this formula gets derived, and you should do this every time. The volume of a cone, therefore, is 1/3 pi. The radius is 5, and the height is 8. So the volume of the cone equals 25, 5 squared. 25 times 8 is 200. 200 times 1/3 is 200 thirds pi. And I'll just leave it at that for now. So there's the volume of the cone. Now I'm going to find the volume of the cylinder. In this case, the volume of the tube equals, volume of a cylinder is simply base area times height. So the volume of the cylinder equals, the base is a circle, pi r squared, that's my B, times height. So the volume of the cylinder equals pi, radius is 4/3 squared times the height, which is what we're trying to find. Okay, so the volume of the cylinder equals 16/9 pi times height. Okay, so we have volume here, we have volume here. We want the cylinder's volume and the cone's volume to be equal. That's how we determine how much of the medium we need, the plastic, to make a solid cone. So I'm going to set these two equal. So you take this and set it equal to that because they're both volumes that we want to be the same. So then we say 200 pi divided by 3 equals 16/9 pi times the height. The pi's cancel because if I divide both sides by pi, I get pi over pi, which is 1, and poof, anything times 1 is itself, so the pi's go away. To get rid of this 16/9, I'm going to multiply by its reciprocal. The 9's cancel, the 16's cancel, I'm left with h on the right. What I do to one side, I've got to do to the other. So I multiply 9 and 9/16 over here. The 3 will make the 9 a 3. 3 times 2 is 600 over 16. So without using a calculator, these are both even. I can easily divide by 2. 300 over 8. Half of 300 is 150. Half of 8 is 4. Half of 150 is 75. Half of 4 is 2. Half of 75 is 37.5. Half of 2 is 1. That reduces to 37.5. And it is centimeters. And that is our height. That is the length of the filament tubing that we need to make this cone of 200 thirds pi volume. Okay. Okay, number 3, a cylindrical desert. Just kidding. A cylindrical dessert, 8 centimeters in diameter, so like a cake, is to be created using a type of 3D printer specially designed for gourmet kitchens. The printer will pipe, or in other words, print out the delicious filling in the dessert as a solid cylinder. Each dessert requires 300 cubic centimeters of filling. Approximately how many layers does each dessert have if each layer is 3 millimeters thick? Okay, so here's what we're doing. I drew this. It is the cylindrical dessert or a cake. And this would be a cross section that is 3 millimeters thick. Now it says right here, the cylindrical, so that tells me it's a cylinder. That's why I drew that. 8 centimeters in diameter makes the radius 4 centimeters. Be careful. So these are 4 centimeters. This is 3 millimeters thick. And the dessert requires 300 cubic centimeters of filling. So that means the volume of this equals 300 cubic centimeters. Okay, the volume of this whole cake. All righty. So What is the volume of a cylinder? Well, the volume of a cylinder equals base area times height. The volume of a cylinder, the volume of a cylinder equals the base, which is a circle, pi r squared, times height. Okay? The volume of the cylinder, we know. That's why I always say, write the formula, substitute the given, simplify, and solve. Write the formula, there it is. Substitute the givens. V, the volume of the cylinder, is 300 centimeters cubed equals pi times the radius, 4 centimeters squared, times the height, h. Okay, we don't know the height. That's what we're trying to find. So when I simplify this, I get 300 centimeters cubed equals pi. 4 squared is 16. Centimeters times centimeters is centimeters squared times height. Okay, I'm going to divide both sides by pi 16 centimeters squared, like so. And watch what's going to happen. Pi cancels pi, 16 cancels 16, centimeters squared cancels centimeters squared. I'm left with h. Okay, centimeters cubed cancels 2 centimeters, leaving me with centimeters 1. 300 divided by 16 pi. Always use parentheses here or it'll do it wrong every time. If I do not put parentheses around this, it'll be 300 divided by 16 and then multiply it by pi, because PEMDAS order of operations says do multiplication and division and then work left to right. So it'd do 300 divided by 16 and multiply the whole thing by pi, which would be the same as 300 pi over 16, and that's not what we want. So we get 5.968. Centimeters equals our height. I'll put h over here. Okay, so if each one of these is 3 centimeters thick or 3 millimeters thick, careful, see how I said centimeters and this is millimeters? All right, so the height of the cake equals the thickness of the layer times the number of layers, agreed? So the height of the cake equals thickness of this cylinder times the number of layers. Think of it as a layer cake. All right. So the height is, let's see, 5.968 centimeters. And that equals the thickness, 3 millimeters, which is 0.03. Okay, made a mistake there. It's 0.3 millimeters is 0.3 millimeters. I'm sorry, 3 millimeters. 3 millimeters equals 0.3 centimeters. Okay, you just move the decimal one place to get from centimeter to millimeter. And then the number of layers we can call n. So when I divide both sides by 0.3, then it will tell me how many layers. So if I take my answer that I have here without rounding and divide it by 0.3, we get 19.89. So it'll take 19.89 layers. So obviously we need to round that up and say the number of layers equals 20. Okay, so that's the answer to that. Page 5, number 4. Hopefully you're getting a feel for this. All right, they gave us a diagram this time. I don't need to draw it. That's fantastic. All right, the image shown to the right is of a fine tube that is printed from a 3D printer that prints replacement parts. If each layer is 2 millimeters thick, so they're talking about this way, 2 millimeters, a layer and another layer and another layer and another layer that are all 2 millimeters thick. Okay, I'll just leave that right here. No, I won't. 2 millimeters thick, and printer prints at a rate of roughly 1 layer in 3 seconds. So 2 millimeters every 3 seconds. How many minutes will it take to print the tube? Now, I want to point something out to you. This is very common in math, especially geometry. Figure not drawn to scale. Do not assume anything from a drawing if it looks like it's 90 degrees or whatever. Okay, so they give us all the dimensions. That's all that's necessary. So the printer prints at a rate of 1/3 layers per second. That is one of the key things. 1 layer in 3 seconds. Okay, so if it's 1 layer in every 3 seconds, it's 1/3 of a layer every second. So let's look at that in a time capsule here. So if this is a time stamp and this is 0 seconds, this is 1 second, this is 2 seconds, this is 3 seconds, and that is 1 layer, that length of time, then in 1 second, it would only print 1/3 of a layer. Capiche? So 1/3 of a layer per second. There's our starting point. Okay. If each layer is 2 millimeters thick, and the printer prints at a rate of that, how many minutes will it take to print the tube? Okay. So what we need to do here is use a formula for distance. Distance equals rate times time. All right. What's our distance going to be? 3.5 meters. Okay. We have millimeters. We have millimeters. We have millimeters. We have meters. Okay. 3.5 meters equals 350 centimeters. And that is equal to 3,500 millimeters. Milli means 1,000. So 2 millimeters is 2/1000th of a meter. So it takes 2,000 millimeters to get 2 meters. All right. So if each layer is 2 millimeters, we could go to all millimeters or we could go to centimeters. It doesn't matter. I will just go to millimeters. So we have 3,500 millimeters, and each layer is 2 millimeters thick. Okay. There's our other piece. Oh, I already marked it. So how can we set this up? How many layers is that going to be? So you take that 3,500 millimeters divided by 2 millimeters, and the millimeters cancel, and half of 3,500 is 1,750 layers. Okay. So we have 1,750 layers to build up to here. So distance equals rate times time. Our distance is 1,750. That's how many layers. 1,750 equals our rate is 1/3 times time. So if we do 1/3 of a layer in a second, and there's 1,750 layers, the time it takes, all we have to do now is multiply both sides by 3. 1/3 times 3 is 1, and I get my time. Multiply this by 3, I get 0. 5 times 3 is 15. Carry the 1. 7 times 3 is 21, and 1 is 22. And 3 times 1 is 3, plus 2 is 5. So I get 5,250. Well, that is per second. So that's 5,250 seconds. Okay. So if I turn my calculator on, 5,250 seconds, how many seconds in a minute? 60. So I can divide by 60, and that'd be 87.5 minutes. Or 1 hour, 60, 27 minutes and a half is 30 seconds. If you want to get really technical. 1 hour, 27 minutes and 30 seconds. Okay, that's how long it would take to print this to me. All right, page 6 brings us to the end of lesson 13. Go to your problem set.